Hi, hello friends. Welcome to my YouTube channel. Now, in this session, I would like to share the solutions of Assistant Engineer Electrical of APTRANSCO AE 2017 paper. The first question on the screen is the main purpose of using core in a transformer is to. Normally, transformer will have two windings. The first one is primary winding and the second one is secondary winding. When the current flows through these windings, it will create a magnetic lines of force like this, that is flux lines, and because of the load also there is a flux lines flowing like this. Okay, so in order to increase the lines of force, we will use the core material in between them like this. Okay, so core is used to increase the flux lines, or you can say decrease the reluctance. Okay, so the suitable answer for this question is C, reduce the reluctance of the common magnetic circuit. And the next question, is a 220 volts separately excited DC motor takes 20 amps current and having armature resistance of 1.0 ohms. A 220 volts, that is 220 volts DC motor with a armature resistance of 1.0 ohms, and it takes a current of 20 amperes, and the armature constant Ka phi is 1.5 radians per second. And what we need to find here is speed, and the speed is in RPM. Okay, and the formula is EB, that's a back EMF, is equal to V minus IA into RA, that is equal to 220 minus 1.0, that is armature resistance, and armature current is 20. We will get 200 volts as EB. Okay, and we know the relationship between the EB and speed is, so back EMF is equal to, that's armature constant Ka into phi into W. So this is speed in radians per second, but the given solution is in RPM, so we will convert this. Okay, so next here, so EB is nothing but 200 volts is equal to the armature constant K into phi is nothing but 1.5 into W. That implies, so 200 divided by 1.5 is equal to, so 2 pi n divided by 60. That implies n is equal to 4000 by pi RPM, and the solution is D here. And next, third question here, a three-phase slip ring induction motor, the slip at some speed is 0.05. The speed is reduced by inserting an external resistance in the rotor circuit, and the slip is 0.15. If the rotor winding resistance per phase is 0.2, the external resistance is. So for this problem, the first slip at some speed is equal to 0.05, and slip at some other speed is S2 is equal to 0.15. Okay, well, normally we know that S1 is proportional to R1, and here S2 is proportional to R2 here. Okay, so R2 is nothing but what we have done here. So R2 is nothing but previously we have some resistance, that is R1, and to that we are adding some external resistance RE here. Okay, from this, so S2 by S1 is equal to R1 plus RE divided by R1. So we know the value of R1. So what is the R1 here? So R1 is nothing but 0.2 ohms. Okay, so from this S2 is nothing but 0.15 divided by 0.5 is equal to R1 is nothing but 0.2 plus external resistance RE divided by 0.2. So by solving this equation we will get RE as 0.4 ohms, 0.4, and the answer is C here. The next question here, when VV or open delta 3-phase transformer system is converted into delta delta system, the increase in capacity of the system is. Normally when we have delta delta system is getting converted into open delta system. Suppose for example say the delta delta system will have 100 kVA capacity. When one winding is open circuited, then we will have 57.73 kVA is the winding is the capacity of this open delta winding. That means this much of capacity is decreased because of when we open the one winding. So now here the given question is, suppose this is 100 kVA and how much will be this increase in capacity. So we have to represent it in terms of in percentages. So normally for example say I will take X kVA here. Okay, so by cross multiplication here X kVA is equal to, so 100 into 100 divided by 57.73, we will get 173.22 kVA. Okay, if you observe here how much capacity is increased here is, so this value is 173.22 kVA. That means there is a increase of 73.2 percentage of capacity. So the answer is D here. And the next question is, 3 kilowatt load is supplied by auto transformer with a 0.7 transformation ratio. That is, they have mentioned K value. Conductively transferred power from primary to secondary winding. So we will substitute the direct formula. The power transformed by conductively is equal to, that is K into, so power rating of 2-phase transformer, that is equal to 0.7 into 3 kilowatts, that is nothing but you will get 2.1 kilowatts, and the answer to this question is A. And the next question here is the sixth question. The number of commutator bars for a 4-pole 2-layer DC lap winding with 24 slots and 1 conductor per layer is. And the solution for this problem is, normally the commutator bars is equal to commutator bars or segments is equal to number of coils. That means one coil will have 2 sides like this. So this is a coil side 1 and the coil side 2 here like this. Okay, here we have commutator bars like this. Normally in the given question we have 24 slots. Okay, so I will take the slot like this. In this slot it's a double layer winding. That means we will have 2 conductors, first conductor and second conductor. So here these two are nothing but conductors. Okay, so these 2 conductors will make one coil. That means 24 slots will make 24 coils. That's nothing but 24 commutator bars or segments. And the solution for this problem is B. Now the next question, the torque developed by any three-phase induction motor at 0.8 per unit slip is. So in the given question, the slip is given as 0.8 per unit. Normally, from the speed torque characteristics of induction motor, we can observe that like this. So here we'll have slip is maximum and slip is minimum here, and the rotor speed is going to be 0 here, and here rotor speed is equal to synchronous speed here. The characteristics will looks like this, okay, approximately. So here up to this point, this region will called as low slip region, where the characteristics are similar to linear characteristics. Okay, as a slip value increases, we will have this one as unstable region, and here we have stable region. Okay, as the slip value increases, we will get a unstable region. So here we have unstable torque produced because of slip is 0.8. Suppose if the slip is say 0.2, then we can say it's a stable region. And the next question on the screen is 8th one. The EB by V, that is a back EMF by supply voltage, is a ratio of DC motor, is an indication of is dash. So normally efficiency is given by output power divided by input power. So here we have output is nothing but we will take the electrical equivalent of mechanical power. So electrical equivalent of mechanical power. Why? Because it's a motor, and divided by, and supply is electrical power, that is electrical power. Okay, so by neglecting the losses, we can write this equation as EB into armature current IA divided by V into IA. So if IA gets cancelled, this is nothing but EB by V indicates the efficiency of the DC motor. Suppose if they asked for V by EB, it will indicate the efficiency of generator. Okay, just like ulta. And the next question here we have is, which of the following test is usually conducted to determine the efficiency of traction motors? So in traction, generally we'll use two types of motors. Traction, first we will use three-phase induction motors, and second one we will use DC motors. In that one also DC series motors. Now in this case, in the given options, we need to find the efficiency of DC series motor. Okay, except the field test, the Swinburne's test, retardation test, and the Hopkinson test are used to find the efficiencies of DC shunt motors and compound motors. Okay, the only option that we left is field test. So field test is a test used to find the efficiency of DC series motors here, that is a traction motors. And the next question here, an 8-pole 50 Hz 3-phase induction motor is running at 705 rpm. So this speed is the rotor speed and has a copper losses of 5 kilowatts, and its rotor input is, first of all, what is the synchronous speed of this induction motor? Ns is equal to 120 F by P, which is equal to, so 120, the given frequency is 50 Hz divided by how many number of poles? 8 poles. This is equal to 750 rpm. Okay, the formula here is the power input to the rotor divided by the power copper losses is equal to 1 by S. So slip is nothing but Ns minus Nr divided by ns, that is equal to 750 minus 705 divided by 750. This is equal to, by solving this we will get 3 by 50 here, and we need to find the rotor input. So power input is equal to, so 1 by s means 50 divided by 3 into the power copper losses is 5 kilowatts. By solving this you will get 83.33 kilowatts. And the next question is, a 3-phase 4-pole 50 Hz induction motor runs at a speed of 1440 rpm. This is the rotating field produced by the rotor rotates at a speed of dash rpm with respect to the stator field. Okay, so what is the synchronous speed here? That is ns is equal to, so 120 f by p, you will get approximately 1500 rpm. Okay, both the fields rotate at synchronous speeds. Okay, so this rotating field rotates at synchronous speed of 1500 rpm, and with respect to stator field, so stator field also rotates at a speed of 1500 rpm. Okay, so when we compare these two, they are rotating with respect to each other with a speed of 0 rpm. Why? Because both the fields rotate at synchronous speed only, so they are at 1500 rpm only. With respect to each other means it is going to be 0. Okay, so because fields. Next question. And the next question, generally crawling in squirrel cage induction motor is a tendency to run stably at a speeds as low as, it is nothing but 1 by 7th of the synchronous speed. Suppose if they ask for cogging is nothing but magnetic locking here, so it is going to be happen at a synchronous speed of 5th. Okay, and crawling at 1 by 7th of the synchronous speed here. Okay, and the next question, it's a very simple question. The starting torque of capacitor start induction motor is directly related to the angle theta between its winding currents by the relationship. So the direct relationship is T is proportional to the phi 1 phi 2 into sine theta, where theta is the angle between these fluxes phi 1 and phi 2 here, and the answer is B here. And next question, the fractional pitch used for eliminating 7th harmonic from the EMF wave of an alternator is, the formula for this one is, the fractional pitch used for eliminating the nth harmonic is equal to, so n minus 1 divided by n into pole pitch. Okay, so normally it will be taken as a 180 degrees electrical, so which is equal to, so 7th harmonic means 7 minus 1 divided by 7, this is equal to 6 by 7, and the answer for this case is D. And here for the 15th problem, I am not able to solve this problem. If you know anybody solution of this problem, please share. And the answer for this problem is it is D, 24.9 seconds. And the next question, and this question here in 16th one, while keeping the excitation constant, if the steam excitation constant here means the kVAR is constant, if the steam supply of an alternator running in parallel with another identical alternator is increased, that means steam supply is increased of one alternator, so which will cause us increase in kilowatt, that is the power supplied by the machine will increase here. Okay, there will be no change in kVAR consumed here. That means it is the portion of the share in the load will increase. Why? Because of there is a direct increase in kilowatt hours. Okay, suppose if you want to increase the reactive power, so reactive power if you have to increase means you have to increase the excitation. Okay, that is the key here. And the next question on screen is the effect of increase in the load on a synchronous motor running with normal excitation is. Okay, if we observe the V curves and inverted V curves of synchronous machine, so on the x-axis we will take excitation, and on y-axis we will take the power factor and the armature current here, like this. Okay, now here, so this is going to be the power factor curve, and this is going to be our armature current. I'm just drawing roughly here. So here we have normal excitation, and the last we have under excitation, and here we have over excitation here. Okay, what is happening here? If there is a effect of increasing load, that means simply we are increasing the IA load on the synchronous motor while running with normal excitation. So normal excitation is somewhere here. So normal excitation is here. Okay, here we are increasing the current value. What about the power factor? So power factor, you can observe it is going to be decreased like this. So the option here is the current IA increases but decrease in power factor. So from these curves. And the next question, the transmission lines are transposed to reduce. Normally on the ideal configuration is like this. The transmission lines are kept like this configuration. So R, Y and B. They are normally transposed, means like this manner, like this, and they will interchange like this. Okay, so in this manner they will transpose. So transposing of lines. Okay, so this transposition is done to avoid the or reduce the interfacing with the neighboring communication lines. Why? Because in normally in transmission lines we will use conductors like this, and also we will use the same tower for communication lines also. So this is for communication and this is for power lines. Okay, so in order to avoid the interference with the neighbor communication lines, we will transpose the conductors. Okay, and the next question here is, if the base current and base voltage of a 345 kV system are, this is nothing but 3000 is nothing but this is the base current and this is the base voltage of a 345 kV line respectively, the per unit voltage and the base impedance of the system respectively. So normally, so V per unit is equal to, so V actual voltage, actual rating divided by V base. Okay, so actual rating is 345 kV divided by how much voltage? It is nothing but 300 kV. So by solving this, you will get 1.15 per unit. And second thing we need to find is base voltage. ZB is nothing but actual voltage divided, not actual voltage, so base voltage, no? So V base divided by I base. This is equal to, so 300 kV divided by 3000 amps. Okay, you will get 100 ohms. So 1.15 per unit and 100 ohms. And the suitable answer is option B here. And next question is, the surge impedance of 60 miles long underground cable is having 50 ohms. For 30 miles the length will be. Okay, the surge impedance loading is independent of line length. So once it is fixed means it will remain as it is. So 50 ohms, it will remain as it is as 50 ohms. Why? Because surge impedance loading is independent of length of the line. Next question. Next question here on the screen. The 21st question. A single core cable is designed to work for a single phase system with a peak voltage of 220 kV. So peak voltage of 220 kV. So V max is 220 kV maximum voltage. The maximum permissible stress in the dielectric is not exceeded 20 kilometers per millimeter. Okay, so the E value you can write, so E max should be equal to 20 kilovolts per millimeter. It should not be more than 20 kilovolts per millimeter. For economical size, so this is a given hint here, that is economical size, the overall diameter of the core. The general formula for this problem is, so E max or E is equal to, so V max divided by R, that is the radius of the conductor, into ln of d by R. For economic size of the conductor, economic size, this term ln of d by R is going to be 1, or d by R is going to be exponential power E here. Okay, so this is going to be 1 here, and E max is nothing but, so 20 kilovolts per millimeter is equal to 220 kilovolts by R here. So by solving this, R is nothing but 11 millimeter. In the given question, we need to find the diameter. So D is nothing but 2 times the radius. This is equal to, so 2 into 11 millimeters. This is nothing but 22 millimeters. Okay, and the suitable answer is option D here. And the last question for this session is, the stringing chart is used for. Okay, so normally the stringing chart is used for finding the sag in the conductors. So stringing chart is drawn like this. So here in x-axis we will take temperature here, and the y-axis we will have tension and sag. So tension and sag here. Okay, so this is the tension curve like this, and this is the sag curve. So this is the sag curve. As the temperature increases, sag will increase and tension will decrease. Thank you friends. If you like my videos, please subscribe my videos and like my videos. Thank you. Have a nice day. Bye bye. Hi, hello friends. So welcome to my YouTube channel. Now in this session I would like to share the solutions of Assistant Engineer Electrical paper of APTRANSCO AE 2017. Now the question is 23rd question. A suspension type insulator has two units with a self capacitance C and a ground capacitance of 0.2 C. Each unit can withstand for a maximum voltage of 11 kV and a string efficiency here. So the percentage string efficiency is equal to, is nothing but the maximum voltage across the string, the total voltage across the string. So total voltage across the string divided by number of insulators in the string, that is N, into the voltage across the insulator nearer to the conductor. The voltage across the insulator nearer to conductor. Okay, so here let's take the pictorial representation here. So here we have a tower and we have capacitance discs here, and here we have capacitance, and here we have conductor here. Okay, so let it name it as C here and C here, and this is 0.2 C here, and the voltage across this one is V1 and across this disc is V2. Okay, so V1 and V2 here. Now here we need to find the value of V2. So the formula for V2 is, so V2 is equal to 1 plus M into V1. So M is nothing but is a ratio of mutual capacitance to the ground capacitance. Okay, so mutual capacitance, self capacitance here. So mutual to the self, sorry. So mutual to self. So here we have, so mutual capacitance is 0.2 C and self capacitance is nothing but C here. So this value is 0.2 here, and V2 is nothing but 1 plus 0.2 into V1. So 1.2 into V1 here. Okay, now the string efficiency is equal to the total voltage across the string is V1 plus V2 divided by number of disk is 2, and the maximum voltage across the string is V2 here. Okay, I will write in terms of V1 here. So I will get 2.2 into V1 divided by 1.2 into 2 into V1. So you will get it as into 100 here. So here also into 100. You will get approximately this one as 91.6% here. Okay, so none of the option is equal to this value. So for this problem there is no solution in the options. The actual answer is 91.6 here. And the next question here is, if a 5-bus test system contains 6 transmission lines and 1 transformer, how many non-zero elements are there in the Y-bus matrix? Y-bus. Okay, so the formula for non-zero elements is non-zero elements is equal to, it is a sum of mutual elements, mutual plus self elements here. Okay, so what is the number of mutual elements? So number of mutual elements is equal to 2 times that of number of transmission lines, that is equal to 2 into 6 is equal to 12. And next one, number of self elements, which is equal to, we have 6 transmission line plus 1 transformer, so 7. So total number of non-zero elements is equal to, 12 plus 7, that is nothing but 19. Option is D here. And next question, 25th one. Here the voltage of a generator and the infinite bus are given as, so E value they have mentioned, so E is nothing but 0.92 at an angle 10 degrees, and V is nothing but 1.0. so V is nothing but infinite bus bar voltage here. Okay, so just observe from here, that is delta is a load angle, so load angle which is greater than 0, that means it indicates that the active power flows from the generator to the infinite bus. Okay, that means active power flows from generator to infinite bus. And second observation here is, the V is greater than E, indicates that the reactive power flows from infinite bus to generator here. Why? Because it's a under excited machine. Okay, so from this, the suitable option that we have is active power flows from the generator to the infinite bus, and the reactive power flows from the infinite bus to the generator. And the next question here, a shunt fault is characterized by, so normally a shunt fault is nothing but a fault occurs means, suppose say for example, so here a line here, transmission line, so here is a fault occurred here. So this shunt fault is characterized by increase in the fault current. So normally current will increase, so as the current will increase, the power factor, that is cos phi, will automatically decrease here. What about the frequency here? So normally at equilibrium accelerating power is 0. Okay, during the fault condition we have acceleration as well as deacceleration, so this is normal condition. But during abnormal conditions, so PA is equal to the shaft power minus electrical power. Okay, so as a fault occurs, I value increases, so that electrical power increases, so that acceleration PA is equal to, so P shaft minus P electrical, well, this value increases, the totally effect is going to be decrease in accelerating power. So this is nothing but deacceleration. So this deacceleration causes reduction in frequency, because of Ns is proportional to F here. Okay, next one. So the option here is increase in current, reduction in frequency as well as in power factor. So option B is the correct one. And the next one, that's 27th question here. A reactance relay is nothing but it's a directional restrained overcurrent relay here. So this is nothing but this is for reactance relay, and this is for Moore relay. Moore relay is a relay which is voltage restrained directional relay, and the last one, the impedance relay. So this is the impedance relay here. So impedance relay is a voltage restrained overcurrent relay. Okay, the reactance relay is nothing but say directional restrained overcurrent relay. So B is the option here. And next one, we have 28th question here. In a 132 kV system, the line to ground capacitance C value you have mentioned. So C is nothing but 0.01 microfarads, and L value given, inductance is 4 Henry here. We need to find what is the value of voltage. We need to find the value of voltage here across the circuit breaker poles. So we have circuit breaker poles here. So let's say this is a fixed one and this one is a moving one. So we need to find what is the voltage across here between these two contacts. If the magnetizing current is to be interpreted is 5 amps. So I is nothing but 5 amps is the current to be interpreted. So general formula is V is equal to I into Z. So Z is nothing but square root of L by C. This is equal to square root of 4 divided by 0.01 into 10 power minus 6, which will give, so 2 into 10 power 3 ohms. So 10 power 4 ohms here, right? Now, so V is equal to I is nothing but 5 into 2 into 10 power 4 volts here. So this can be written as 100 kilovolts. So the option is D here. And next one, important question and a repeated question here. The inertia constant of two group of machines which swing together, M1 and M2, and that inertia constant of the system. So when they are swinging together, its equivalent will be M1 plus M2. Suppose if not swinging together, then M1 M2 by M1 plus M2. So if this is the option here, suppose if this is not, means choose this answer, right? And next problem. Next, the per unit synchronous reactance of a machine is 1.6 per unit the short circuit ratio. Normally the short circuit ratio is inversely proportional to the synchronous reactance. So that implies 1 by 1.6. So it's approximately will be 0.625, and D is the answer, right? And next one, the precise control of reactive current flow entering the transmission line and distribution systems can be minimized by using, we can use the static wire compensators as well as Thyristor switched reactors. So both are the correct options for this answer. That is static wire compensators and D. B and D both are the correct answers. And next question, that is 32nd question here. The sending end voltage and receiving end voltage are mentioned here in the transmission line. That is, what is sending end voltage? So Vs is equal to 10 into 10 power 3 volts per phase, and receiving end voltage, so Vr is equal to 9.5 into 10 power 3 volts per phase, and the voltage drop, that is I into R drop, is nothing but 150 volts per phase, and the receiving end power factor, so cos phi r is equal to 0.8. So what we need to find here is cos phi r. So cos phi, yes, we need to find here, question mark. Okay, the formula from the phasor diagram we can derive directly here, that is, so cos phi r, so cos phi, sorry, is equal to, so voltage VR into cos phi r plus I into R drop divided by Vs. So what is the VR value? So VR value is 9.5 into 10 power 3 into 0.8 plus 150 divided by, so 10 into 10 power 3. Okay, So by solving this, 7600 plus 150 divided by 10 into 10 power 3. Okay. So we will get it as 0.775. 0.775 is a 5, and normally the power system will have lagging power factors generally by default. Okay, so 0.775 lagging is the answer. Okay, and next question. A DC distributor of length L meters and resistance R ohm per meter fed at both the ends with the equal voltages and uniformly distributed with the I amps per meter. Then the power loss in the distributor is I square or L cube divided by 2 here. So this is the option. Okay, if they ask it for what is a voltage drop, and this is the answer here. So you can go through this derivation in power systems book by VK Mehta. So power system by VK Mehta, and the page number is 330. Next one, the corona. Okay, the corona losses in a transmission line are reduced by using the bundle conductors. This is a general question here. Okay, so this is done because the critical disruptive voltage, that is here Vc, is proportional to radius of conductor, and the power losses is proportional to, so V phase voltage minus Vc whole square, as bundle conductors increases the radius of the conductor, which will increase the Vc value. As the Vc increases, so power losses is proportional to Vph minus Vc. So as Vc value increases, square means the total value going to decreases here, that is power losses decreases here. So power losses is nothing but corona losses. Okay, so corona losses by using is reduced by decreasing the increasing the radius of the conductor here. Okay, right. And the next question, next 35th question, a 4000 kVA star 11 kV or 132 kV delta star connected transformers. So primary winding is delta connected, secondary winding is star connected. 11 kV or 132 kV transformer, its rating is 4000 kVA transformer, and having a reactance of x1 is equal to 0.12 per unit. You need to find the actual value of x1 here. Okay, so how can you find the value of x1? So x1 is nothing but x actual value. So x per unit is equal to x actual value divided by x base value. So from this x actual value, what we want is equal to x per unit, that is 0.12 into x base value. So what is x base value? So x base is nothing but v base square divided by s base, that is equal to 0.12 into, in terms of xb, xb is v base square. So what is v base here? That is 11 kV. So 11 kV is nothing but 11 into 10 power 3 into 11 into 10 power 3 divided by, so 4000 into 10 power 3 here. Okay, and so 10 power 3 gets cancelled here, and here, so 4000 means this one gets cancelled, that is equal to 0.12 into 121 divided by 4. So 4 1 ja 4, 0.03. So we'll get the answer as 3.63 ohms as the answer. So 3.63 is the answer here, right? And next question, the number of comparators required in a 4-bit comparator type A to analog to digital converter is, the formula, simple formula here is, the number of comparators required is for a n-bit comparator ADC converter is, so 2 power n minus 1. Okay, that implies here in the given question we have 4 comparators, that is n is equal to 4 here, so that the number of comparators is equal to, so 2 power 4 minus 1. So 2 power 4 means 16 minus 1, that is equal to 15 here. So 15 is the answer. Next one. In a 5-bit weighted resistor digital to analog converter, the resistor value corresponding to LSB is, so our LSB is 40 kilo ohms and the resistor value corresponding to RMSB is question mark. Okay, so here the relationship between RLSB and RMSB is, so RLSB is always greater than RMSB. This is a hint to remember. So RLSB is equal to, so 2 power n minus 1 into RMSB. So here this is equal to, so 2 power n is nothing but how many? 5. So 5 minus 1 into RMSB. So here RLSB is 40 into 10 power 3. Okay, so from this RMSB, so RMSB is equal to, so 40, and you can write kilo here, divided by, so 2 power 5 minus 1 means 2 power 4, that is 40 divided by 16 into 10 power 3, that is nothing but 2.5 kilo ohms is a resistance. So option here is D is the correct answer. And the next question, that is 38th question here. So this question is a question which is asked in GATE 1995. So asked in GATE 1995, and for this is for EC branch question here. A switch tail ring counter is made by using a D flip-flop. The resulting circuit is, so let's take a D flip-flop here. So here we have Q and Q bar. In this case here we have taken the output from the Q bar circuit, Q bar here, and which is connected to a AND gate, and here we have a clock pulse. Okay, and this circuit acts as a T flip-flop. And the next one, 39th question, the address latch enable line of an 8085 microprocessor is used to latch the 8-bit address lines, that is 87 to 80, that is a 8 lines, into an external latch here. And the next question, 40th one, which diode exhibits the negative resistance characteristics? Generally the tunnel diode will have the negative resistance characteristics when compared to Zener diode. Okay, so tunnel diode is the answer here. And the next one, a closed loop transfer function of a unity feedback system is given by y of s by r of s is equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. This is a second order system. The system kV is given by, so the formula for kV is given as, so kV is equal to limit s tends to 0 s into g of s. So s into g of s is nothing but open loop transfer function, but the given question is they have mentioned that closed loop transfer function. So how can you get the open loop transfer function? YLTF is equal to closed loop transfer function divided by 1 minus closed loop transfer function. So if you done this, we will get omega n square divided by s square plus 2 zeta omega n into s is the answer. So this is nothing but g of s. So here kV is equal to limit s tends to 0 s into g of s is nothing but omega n square divided by s square plus 2 zeta omega n into s. Okay, for further simplification I will make a s common here. So s into omega n square divided by s into s square plus s, if you make a common here, s plus 2 zeta omega n here. So let's just get cancelled here. So here I forgot limit s tends to 0 here. That implies, so limit s tends to 0, omega n square divided by s plus 2 zeta omega n here. If you substitute s is equal to 0, then the kV is equal to omega n square divided by 2 zeta omega n here. If omega n gets cancelled, omega n divided by 2 zeta is the answer. So this is the answer here. And next question. A unity feedback system has a open transfer function of g of s equal to k into s plus 1.1 into s plus 2.2 divided by s into s plus 3.3 into s plus 4.4. Okay, at k is equal to 0, closed loop poles. So first of all, we will get the closed loop transfer function is equal to open loop transfer function divided by 1 plus open loop transfer function. And after doing this, we will take the characteristic equation. So what is a closed loop transfer function? So CLTF is equal to, so k into s plus 1.1 into s plus 2.2 divided by s into s plus 3.3 into s plus 4.4 here, plus, so k into s plus 1.1 into s plus 2.2 here. Okay, so the open loop poles when k is equal to 0. So as k is equal to 0, okay, at k is equal to 0, what is happening here means this total term is going to be 0 here, and we have poles at s is equal to 0 and s is equal to minus 3.3 and minus 4.4. So these poles are real and distinct. They are not complex or they are not repeated. So the option A is the correct option here. So here we have, so minus 3.3, minus 4.4 and 0 here, right, in the explain. Next question here. A unit impulse, right, unit impulse to a linear network has a response r of t. So let's consider a linear network is there. For linear network, first we have given an input, that is unit impulse we have given, and we got the output as r of t. For the same network, now we have changed the input. Now this time we have given unit step you have given, and we get the response as s of t. So s of t. The relationship between r of t and s of t we need to find here. Okay, the relationship is r of t, that is a ramp output ramp response, is the differentiation of step response. Okay, so d by dt of s of t. So directly we can write this answer. Okay, and next one, 44th question. The phantom loading for testing of energy meter is used for. Generally, the phantom loading is used for large machines which are having high current capacity, which are not practically available in laboratory. Okay, so the phantom loading for testing of energy meters is used for to test the meters having a large current rating, for which loads may not be available in the laboratory. Okay, and next question here, and this is 45th question. The ratio of rotor reactance x to the rotor resistance for two-phase servo motor is less than that of the normal induction motors. Okay, that is x by r ratio of two-phase servo motor is less than the x by r ratio of three-phase induction motor. This is a solution, right? And the next question, a track in a single phase circuit taking V volts and operating at a firing angle of alpha is supplying a resistive load R. The power losses in the circuit is going to be, so V square by R, and this is a C is the answer for this, that is V square by pi R into pi minus alpha plus sine 2 alpha by 2 is the answer here. And the next one from power electronics, in a boost chamber circuit, if Vs, V0, L are the input voltage, output voltage and inductance respectively, when the conducting switch is open circuited, the rate of change of inductive current is Vs minus V0 by L. And this is the option here. And the next question directly is, in a three-phase converter circuit during the commutation, when the one SCR is in one phase, turn it on to turn off the other SCR. That means we have, suppose say here is a switch and here is the same switch, so S1 and here say S3. So when we want to turn on the switch, one switch, this is a turn on means, so in order to turn off this switch, but for a short period of time these two switches are conditioned, that is S1 comma S3 on condition. So when S1 switch and S3, so both are on condition, that means it will short circuit the source and the load. So short circuited means current will be maximum value and the voltage will be minimum or zero value. So this phenomena is called voltage notching here. And next one, the 49th one, a snubber circuit is connected to the power semiconductor devices in order to reduce. Normally snubber circuit are used to protect from the electrical stresses. So what are the electrical stresses we have here? That is, first one is dV by dt and second one is di by dt. So if it's not protected means then we will have hot spots in the thyristor and it will get damaged here. So dV by dt is a protection given by using capacitor and di by dt by inductor here. So inductor is connected in series and capacitor connected in parallel here across the resistance. Okay, thank you friends. If you like my video, please subscribe and comment on my videos. Thank you. Have a nice day. In the next session we will discuss remaining technical questions from the APTRANSCO AE 2017 question paper electrical. Thank you. Hi, hello friends. Welcome to the last session of APTRANSCO AE electrical solutions. In this session we will discuss the question number from 50 to 70 technical paper. And the question is, which of the following is present in thyristors but absent in BJT, MOSFET and IGBT? Thyristor is a thyristor, or I can say SCR. So SCR is a current latching device. So latching device. Okay, so which is not present in BJT, MOSFET and IGBT, and the solution is latching here. Okay, and the next one, that is the question is 51. The fifth harmonic component of induced voltage in three-phase alternator can be completely eliminated by using the winding of pitch. So we have seen the formula earlier, that is, in order to eliminate the harmonics we'll use n minus 1 divided by n into pole pitch here. So this is one, we are going to eliminate fifth harmonic, so 5 minus 1 divided by 5, that's nothing but 4 by 5. The option is here is B here. And the next one, 53rd one, in an adjustable speed AC drive, which quantity gets reduced above the rated speed? If you take the characteristics above and below rated speeds here, so normally at here, so below rated speed here and here above rated speed. Below rated speed it is nothing but a constant torque variable power. So let's take the torque here. So torque is constant here like this. After that torque is going to be decreased like this, and here we have variable power. So below rated speed we have variable power, after which we have constant power here. So this is for power and this one is for torque. So from this you can observe that in an adjustable speed AC drive, which quantity gets reduced above rated speed is nothing but torque. So reduced starting torque is the answer here. Next one, that is 53rd one, that is RC triggering is preferred over the resistance triggering. So resistance triggering is enables us over a firing angle of 0 to 90 degrees only. That is RC triggering will enables it to extend to around 180 degrees. Okay, it enables triggering at larger values of firing angles here compared to RC triggering here. So it is around 0 to 180 degrees. Okay, ideally, not practically. And next one, 54th question here, that is from the measurements, a moving coil meter has a resistance of 3 ohms and gives a full scale deflection of 30 milliamperes. To measure the voltage up to 300 volts, the external resistance should be connected in series with the instrument is. So the formula that you'll write here. So I'll write here itself that RS is equal to Rm into m minus 1. So here m is nothing but capital V divided by Vm. That is equal to, in the given problem they have mentioned that what is the voltage to be measured is 300 volts divided by how much value of deflection, scale deflection is, it is nothing but 30 milliamperes. Okay, so 30 milliamperes, that is 10 power minus 3, but we want voltage. So what is the resistance is nothing but 3, so we get the voltage here. So from this we can write 1000 into 10 divided by 3 here. So this is the value that we got. So from this is equal to, here right, so Rm is 3 ohms into m value is 1010 divided by 3 minus 1. So this is equal to 3 into 10000 minus 3 divided by 3. So finally we'll get 9997 ohms as the answer. So option A is correct here. And we will move to the next problem, similar kind of problem here, but small variation here, that's it. So a PMMC instrument has a full scale deflection of 100 microamperes and a coil resistance of 1 kilo ohm. To convert the instrument into an ammeter with a full scale deflection of 100 milliamperes, the required shunt resistance. The formula here, that is shunt resistance, is RSH is equal to Rm divided by m minus 1 here. So here m is equal to 100 into 10 power minus 3 divided by 100 into 10 power minus 6. So this is because m is nothing but how much value you have to measure. So higher value 10 milliamperes divided by 10 microamps. So this is equal to 1000. Okay, so now Rm divided by m minus 1. So Rm is how much? 1 kilo means 1000 divided by 1000 minus 1, so approximately equal to 1. Okay, so the option approximately equal to 1 is nothing but 1.01, that is 1.001 here. Ohms is the answer. Okay, and the next question, that is 56th question here. When measuring insulation resistance of cables using DC sources, the galvanometer should be initially short circuited because the cables will have high amount of capacitance. So I is equal to C into dV by dt here. So as is high amount of capacitance here, when sudden changes happens, that means because of this one we will have a huge amount of current. So cables will have high value of capacitance which draws a high value of charging current through it. So that is the reason why we will short circuit the galvanometer. We initially short circuited here, right? Next question, the self inductance of a coil can be measured by using which of the following bridges here. Normally just Wien bridge is used for measurement of frequency. So it is used for measurement of frequency, and sharing bridge is used to measurement of capacitance. Okay, and Wheatstone bridge is used for medium resistance. Okay, and the only option that we have left is Anderson bridge is used for self inductance. So option is C is the Anderson bridge is used for self inductance of a coil. And the next question, which is a direct question from the A.K. Sahni textbook. Okay, so here a 200 volt 5 ampere DC energy meter is tested at its market ratings. The resistance of the pressure coil is 8000 ohms and that of current is 0.1 ohms. The power consumed when the testing of the meter with a phantom loading with the current circuit excited by 6 volts battery is. So here first of all we have two coils, so power consumed by potential coil. So power consumed by power consumed by potential coil is equal to, so V square by RP. That is, what is V square? So V square is nothing but, so 200 into 200 divided by potential coil is 8000. Okay, if we solve this, we will get 5.5 watts. And next case, power consumed by current coil, so which is equal to, what is the current rating? Is nothing but 5 amps into 6 volts battery, 6 volts, that is nothing but 30 watts. Okay, sorry, here this is 5 watts only, right? So 5.0 here, right? So 30 watts. So total power, consumed is equal to, so 30 plus 5 is equal to 35 watts is the answer. So option here is, we have D, here's the option here. And next question here, a system shows zero steady state error, that is ESS is going to be 0 here. So ESS is 0 for step input, and finite steady state error for ramp input, and infinite steady state error for parabolic input. So let's take the table here. So ESS values for here, so first I will take type 0, 1, 2, and ESS here, that is for step input and ramp, and last one parabola. Okay, so first one we have, so 1 by 1 plus here K position error, and here we have infinite here, and here we have 0, 1 by kV, and here we have infinite, and 0, 0, 1 by K, K A here, right? So then the given question, a system shows zero steady state error for step input, so zero steady state error for step input, 0 here, finite steady state error for ramp input, so finite value here, and infinite error for parabolic input. So this is a type 1 system. From the table we can directly write the solution here. And the next question, after drawing the root locus, the closed loop poles corresponding to a specified value of gain K. Okay, after drawing the root locus, the closed loop poles corresponding to specified value of gain K can be determined from which of the following criteria. So we will use the magnetic criteria alone to find these values, right? So option A is the answer. And the next question, the open loop transfer function of a unity feedback system is given by, so G of S is equal to K into S plus 13 divided by S into S plus 3 into S plus 7 here. So here what we need to find here is the allowable maximum value of K for the closed loop system to maintain stable here. So here we will use the RH criteria here. So in order to find the RH criteria, first we need to find the closed loop transfer function. So closed loop transfer function is equal to, so K into S plus 13, directly I am writing here, so S into S plus 3 into S plus 7 plus K into S plus 13. Okay, so from this the characteristic equation, so characteristic equation is can be written as, so I will write directly here, S cubed plus 10 S square plus 21 plus K into S plus 13 K is equal to 0. So if you draw the RS table here, so S cubed and S square, S power 1, and you have S power 0 here. So first term is 1, and the next term is 21 plus K, and here next term is 10, and here 13. So by cross multiplication here, so you can get it as, so 10 into 21 plus K minus 13, here I forgot to write K here, so K divided by 10. Okay, so this term I will write it as a, suppose say for example say a here, I will write a here. So the a value should be greater than 0 for stability or stable. Okay, so now next I will do is I will take this value, that is 210 plus 10k minus 13k should be greater than 0. Okay, that means so 210 should be greater than 3k here. That means k value should be less than 70, but in the given question the allowable maximum value of k is 70 only. If you choose an 80, then the system will become unstable. So k value should be less than 70 or equal to 70 maximum value here. And the next question, the frequency and voltage in dielectric heating are, the frequencies are going to be from 10 to 30 megahertz and up to 25 kV, and A is the answer here. And the next one, the trapezoidal curve is a close approximation in mainline services. Why? Because trapezoidal is for mainline services, and quadrilateral curve for urban services approximation values. Okay, a close approximation to the mainline traction services. Okay, not an exact approximation only. Okay, and the next one, the pantograph is a device is used to supply AC to the transformer of locomotive. Okay, so used to supply AC to the transformers. Generally we can observe this when the railway system, traction system. Okay, so here we have a track here. On behalf of on the top of it we have power lines like this. Okay, we will connect a pantograph which will take the supply from the AC supply and give it to the locomotive here. Okay, used to supply the AC to the transformer in locomotive. That is the answer here. And the next one here. So in the given problem, we need to find the values which are not ZA or ZB and ZC. That means here we have a star network which is converted into delta network. So we have star is converted into delta here. So just I will take this as 10 ohm resistor, and here I will take this as J5, and here I will take a 20 ohm resistor like this. So these are nothing but, so here ZA, ZB and ZC should be found here. So what is the value of ZA? ZA is equal to, so 10, that means I'm going to make into delta here. Okay, so delta means from this point to this point, and from this point to this point. Here we have, so this is ZA, ZB, and here we have ZC here like this. So ZA is nothing but, so here ZA is equal to, so 10 plus 20 plus 10 into 20 divided by J5, that is equal to, we may get 30 minus J40. That's the option available here, but we want to find what is, which is not ZA or ZB or ZC. So this option is not right, and take ZB here. So ZB is equal to, so J5 plus 20 plus, so J20 into 5 divided by 10. So that's nothing but 20 plus J15, which is option also available here. So this is not the option, and ZC here we may get, so J5 plus 10 plus J50 divided by 20, that is nothing but 10 plus J7.5. so this is also not the correct option, and the only left option here is, the correct option is D is the right option here, so which is not ZA or ZB or ZC here. And next one, A network is said to be resonance when the voltage and current in the network input terminals are going to be in phase or out of phase, in phase with the quadrature, in phase, and have equal magnitudes. So it is nothing but out of phase. So in phase means we have in phase means we have 0 degrees, out of phase means 180 degrees. So okay, that means when at the resonance condition XL is equal to XC, the network will have only resistance here. So resistance means it is a purely resistive network, so power factor is going to be unity. That means the voltage and current waveforms are in phase quantities. Okay, in phase quantities, out of phase means 180 degrees. So option here is A is the right option. And the next question, the internal resistance of an ideal voltage source is. So here there is a confusion between the voltage source and the voltmeter. So generally for voltmeter we should have internal resistance should be infinite. So for voltage source our internal should be 0 here. Okay, and from this the answer is ideal voltage source means it will have internal resistance is 0. So option B is the correct option here. And the next one, and the next question, 68th question here, the time period of a third harmonic power supply frequency in milliseconds. Normally we'll compare the fundamental frequency here. So first we will take the fundamental frequency. So this is the fundamental quantity. Okay, let's say F is 50 Hz and the time period is 1 by 50 seconds here. Now here the third harmonic means it will have 3 times supply frequency. That means here we'll have 1, 2 and 3 here, and 1, 2 and 3 here. That is 3 times supply frequency. So the time period of 3 third harmonic is equal to 1 by 3 into 50 seconds here. So this is nothing but 6.66 milliseconds. The option here is C is the right option. And the next question here is the power consumed by a balanced 3-phase load measuring 2 wattmeter method. Okay, the meter readings are 8 kilowatts and 4 kilowatts respectively. The power factor of the load is going to be. So generally the power factor can be found by using the formula. Say active power, no? So active power means we'll use the formula. So theta is equal to, so tan inversion of W1 minus W2 divided by W1 plus W2 into root 3 here. This is the general formula here. So W1 W2 are 8 and 4 kilowatts respectively. That means theta is equal to, so tan inversion of, that is 8 minus 4 kilowatts divided by 8 plus 4, that is 12 here, into root 3. That is equal to, so tan inversion of, that is we'll get 4 by 12, that means root 3 divided by 3, you can get theta as 30 degrees. So power factor is nothing but cos theta, that is equal to cos 30, that is equal to 0.866. But in the given option, in between the value of 0.52 unity. So from 0.52 unity will exist a value of 0.8666. So this is the answer. D is the answer. Okay, and the last question of this session is, which of the following statement is incorrect? Here the superposition theorem is useful for linear only. It's not valid for non-linear elements. What? So this is the statement is incorrect. Analysis when the several sources are present in the circuit. So this is the first option. And Norton's equivalent network consists of one current source in parallel with an independence. Okay, actually it should be impedance actually. So this is a spelling mistake. So you can also choose this one also as per the key given by APTRANSCO. Okay, so first option is A is the option here. Okay friends, thank you friends. So thank you for watching my videos and giving comments. If you like my videos, please subscribe my videos and comment on my videos. Thank you.